To finish up chapter 12, we're going to discuss fairness criteria for elections and election methods. And we're also going to discuss districting and redistricting, as well as voting power per person. So we'll start with fairness criteria for elections, which I believe is section 12B in the textbook. It's all lumped together in chapter 12 in these notes. So judgments of fairness are more or less subjective, right? But aside that being the case, mathematicians and political scientists have come up with some criteria that more or less make sense when it comes down to judging the fairness of an election, right? And though I don't have any examples to work with these, I can at least introduce these concepts. So, we saw in the previous video and in section 12A different voting methods for sequential runoff, plurality, point systems, things like that. Now we need to judge which one of those is maybe the better method. So one way to do that is to consider these fairness criteria for an election. So we have 4 criteria. We'll be asked in problems in the homework in these sections to determine whether or not an election or a statement about an election makes sense in terms of, or is fair in terms of one of these 4 criteria. So criterion 1 says that if a candidate receives the majority of the first place votes, that candidate should be the winner. That's a pretty sensible criterion for fairness, right? A candidate that receives a majority of first place votes should be the winner. I think most of our previous methods satisfy that. Maybe not the point system. That would be one that might break that rule sometimes. So if a candidate is favored over every other candidate in pairwise races, that candidate should be declared the winner. Okay, so of course, the pairwise candidate method satisfies that, right? We use that as one of the methods to determine the election on the ranked ballots, and that method would, of course, obviously satisfy this fairness criterion. Now we might see that the point or sequential runoff systems actually don't satisfy this in all cases. Now it's important to note that a lot of these voting methods don't satisfy all criterion in all voting outcomes, but it could be that sequential runoff or a point system might actually, in a particular election, happen to satisfy all 4 of these criteria. It's just whether or not they will generally always do that. And that's a very interesting question that we're going to end this page on with an answer. So criterion 3 is suppose that candidate X is declared the winner of an election and then a second election is held. So this gets a little bit more abstract. If some voters rank X higher, so if X was the winner, and then in the second election, some voters rank X higher in the second election than in the first, in other words, X gains some ground with voters, and there are no other changes to the orders of the candidates, then X should also win the second election. That would make sense, right? If we had a second election and one of our candidates, if our winning candidate of the first election, got even higher regard or higher rankings from people, then of course that candidate should win the second election. So criterion 4, suppose that candidate X is declared the winner of an election and then a second election is held. So similar to criterion 3. If voters do not change their preferences, but one or more of the losing candidates drops out of the race, then X should also win the second election. Right? Maybe this one's a little bit harder to imagine, but it shouldn't affect the election that there were candidates beneath X that have dropped out of the race, right? So if in another reality there was another election, that's the second election, right? And in that reality, voters did not change their preferences, but they didn't have the other candidates to vote for, some of the losing candidates that were in the election. Not all of them, of course, but one or more of the losing candidates were not in the alternate realities election. Then candidate X should also win that second election. And though these are sort of exotic examples and situations to create or to come across in elections, they can happen. And it turns out that in trying to meet all 4 of these election criterion, no voting method can actually do that. no voting system can actually satisfy all four of these criteria. And the key statement here is in all cases. And this is really interesting that this is actually a mathematical theorem. This has been proven mathematically, Arrow's impossibility theorem, that no voting system can satisfy all four of these fairness criteria in all cases. And what we mean by that is in every single election that might ever be held. Okay, so with these, with those voting methods we saw, those are all voting systems. So of course, you know, there can be cases for any one of the previous 5 voting systems we looked at. There can be cases, individual elections in which not all 4 of these criterion are satisfied. Now, on the other hand, there can be cases where all 4 criterion are satisfied or most of the criterion are satisfied and otherwise. So that's a really interesting idea. So it really does make the question a bit stickier, right? So we don't have an obvious answer for the best election method, particularly if we accept these 4 criterion as the gold standard of fairness. There's no system that can satisfy all 4. So we have to sort of empirically or by experience choose the ones that seem to work out the best and be the most fair. I would venture to say that even though the plurality method satisfies, I think, always 2 of these conditions, and I forget which 2 exactly. I believe maybe this and this. I forget which ones really, but it satisfies at least 2 of these criterion. Despite it doing that in all cases, I think that, you know, when we look at all cases of the plurality method, I think we see a lot of voter dissatisfaction. So anyway, that's just my 2 cents on plurality. So let's get to voting power. So in other words, how much voting power does an individual have, perhaps in a given state, right? So remember that, you know, each state has electoral college votes or electoral votes towards the presidential election. Also, remember that those electoral votes are also the same number of representatives that each state has to go to Congress for them. So, you know, when we talk about electoral votes, we're also talking about congressional representation. So each one of these single electoral votes of California's 55 electoral votes, also we have one congressional representative, you know, that is sort of corresponds to that electoral vote. So in other words, California has 55 congressional representatives that go to the House of Representatives to vote on laws and write and propose new laws. Whereas similarly for Wyoming has 3 electoral votes in the presidential election, and they also in turn have 3 congressional representatives in the U.S. House of Representatives. So these electoral votes, or we can think of them as congressional representatives, they all represent the population of each state, right? Or they represent their district in each state. But what we'll do is we'll sort of homogenize them, because in the presidential election, you know, the presidential candidates win either all 55 of California's electoral votes or 0. Same thing for Wyoming, all 3 of Wyoming's electoral votes or 0, right? Nobody gets to split California's electoral votes. Wyoming doesn't split its electoral votes either. Nebraska and Maine do in some sort of funny way, but they're the only 2 states that do that. So the question then is this. You know, the reason California has 55 and Wyoming has 3 electoral votes is because it is based on population. And there's a question as to, you know, how fairly is it based on population, right? So let's take that into account. Let's have a look at this. The populations of the 2 states were approximately 39.8 million in California and 577,000 residents, respectively, in Wyoming. So almost 40 million in California and just over 500,000 in, or a bit over 500,000 in Wyoming for people here. So what they ask us to do is they say, in terms of electoral votes per resident, contrast the voting power of California and Wyoming. So clearly California has more people. They have more electoral votes as well. But let's think about this in terms of each individual in California. how powerful is an individual's vote in California compared to one in Wyoming? And the way to think about that is to normalize these values. In other words, they say, and the problem says to use electoral votes per resident, but that would be a small number. So I'm going to do residents per electoral vote. So let's have a look at that. So the California residents per electoral vote. So that literally tells me to divide my number of residents by my electoral votes for this state. And when I do that, I get this 723,636 and then 0.36 residents per electoral vote. Rounded to 2 decimal places, but we could have rounded to the nearest whole number. So let's think about what this number means. So it means that for every 723,000 people in California, they have one electoral vote. So their vote is mixed in with 723,000 people. They're one of 723,000 people going to, within that electoral vote. Now, on the other hand, let's look at Wyoming's residents per electoral vote. Wyoming has 500 or had 577,000 residents in the 2020 election. They had 3 electoral votes in the 2020 election. And so their residents per electoral vote comes out to 192,333.33 residents per electoral vote. So again, let's put that number in context. So for each electoral vote that comes from Wyoming, that electoral vote comes from 192,000 voters. So if you're a voter in Wyoming, then you're one of 192,333 voters who chose this electoral vote. Your voice is less diluted in this case, right? You're one of 192,000, whereas in California, you're an individual of 700 among 723,000 other voters deciding on a single electoral vote. So you have less say in the election in that sense, right? When you're in this group, you're in a bigger crowd. So you have, in some sense, you have fewer electoral votes as an individual, right? 723,000 people are sharing this one electoral vote in California, whereas 192,333 residents are sharing this electoral vote in Wyoming. So another way to say that is this, down below. So one electoral vote in California in the 2020 election accounted for, and I just divided this number by this to get however many times this number is than this one. And we get that one electoral vote in California accounted for 3.76 times as many people as one electoral vote in Wyoming. So again, what that means is for every one person in Wyoming's voice, there are 3.76 people in California who had to combine their voices in order to get, to match the electoral vote. So in some sense, we could say that Wyoming's, a voter in Wyoming has 3 times the power, or 3.5 times the power as a voter in California in terms of the electoral vote. So that does seem a little bit jilted, or tilted rather, a little skewed. So that's this idea of voting power, right? So again, you'd want this number to be low. And maybe for an extreme example is this, perhaps you're in a state of one. There's one person in your state, you have one electoral vote, you're that person, you get that electoral vote, you're in complete control of that electoral vote. That's a very powerful position, right? If you have one whole electoral vote to your name to put towards the presidency of the 538 that are available, then that's the most powerful position unless you had multiple, right? So that would be more powerful than any one of these. So the smaller this number is, the more power the residents of this state have. And it looks like, in this case, California is quite a bit more diluted than Wyoming's voters. So that's, one way of measuring voting power in the United States, and it's an interesting thing to look at. Another scenario is congressional representation, and then how this can be problematic as well. So the U.S. House of Representatives, again, that 538 Congress people, a certain, fixed number from each state based on population. They all come from districts within their states. Okay, every 10 years, the congressional district maps are redrawn based on the census. This is called redistricting, and we hear about it a lot in the news, and a lot of people like to complain about it, and it becomes a pretty political issue. And really, in recent history, the process has become fraught with partisan influence and just sort of lots of political fighting in general. So one of the issues is this: the party in control of each state legislature is allowed to pick its district, right? They have the most influence on the redistricting process, and this is true for pretty much all states in the country. So say if the Democrats are in control of the state legislature of a state, when it comes time to draw this map based on the US Census data, well, they're able to draw the map in such a way as to favor their party. And what we'll do it as the very last example we look at, or examples we look at in this set of notes in this video, is we'll actually see how we can draw maps in ways that will favor one party over another, or how to draw perhaps a fair map, and to help things be as expected. Now, I think that we would all expect that a fair map would have some sort of relevant or some semblance of what the popular vote in the state was. If half the population of the state voted for Democrats and the other half of the population voted for Republicans, we would expect a half and half split between Republicans and Democrats in their congressional representatives. Now, again, that doesn't happen all the time because these maps can be drawn, and they're drawn in such a way as to favor one party over the other, and that, of course, is called gerrymandering, as we're all most likely aware of. So let's look at an example of this. In the state of North Carolina, it has 13 seats, or congressional representatives, and its redistricting process is controlled by its state legislature. So in 2000, the Democrats happened to control the state legislature, and they drew the maps for the elections from 2002 to 2010. And then following the 2010 census, the state legislature was controlled by Republicans. So they won back the state legislature. These are congressional representatives in a state Congress, not federal Congress, right? So they're the ones who write the maps. They're smaller time politicians than the Congress people that we see in Washington, D.C., going to the Capitol building. But nonetheless, they have this powerful job of drawing maps. So typically, they'll draw these maps in favor of their own parties. So the Republicans controlled the state legislature in 2010, and they drew the maps beginning with 2012, elections beginning in 2012. So we have the table below that gives us the two elections: a 2010 election on a Democrat drawn map and a 2012 election on a Republican drawn map. So let's see how these parties, or these state legislatures, might have tilted the scales or tilted the maps in favor of their own parties. And we'll see that both parties actually did that in this case. And we're going to calculate how we might go about doing that. So they asked us to assess the information for the balance between the popular vote earned by each party and the number of representatives that are actually earned or won by each party in each election. So again, remember that the way these elections take place is as follows. Among the 13 representatives in North Carolina, each one of those seats has a district associated with it. In other words, a set of neighborhoods or an area in the state. So if you live in a certain area of the state, you vote for a certain congressperson. And what we see is, in this result here, it's just the statewide vote. So again, like I said, in a fair map, in a fairly drawn map, then what we would expect is the overall percentages. So we see in 2010 that 45% of the vote statewide went towards Democrats, and 54% of the vote statewide went towards Republicans. So we should see something similar to that in the number of House members elected for each party. However, when we look at this at just first glance, we realize this: statewide, only 45% of the population voted for Democrats, whereas 54% of the population voted for Republicans. However, so the majority of people voted for Republicans. However, 7 Democrat House members were elected and only 6 Republican. So this already doesn't add up. Democrats got more than half of the seats for Congress. However, they got less than half of the vote statewide for their party. So in other words, among all the votes in the state, 45% of the votes cast were for a Democratic candidate. So this clearly raises an eyebrow, right? We should look at this and say, okay, this doesn't seem fair. Well, to calculate it exactly, we look at this. We look at this percentage, and we should say, okay, Democrats should have expected about 45% of the 13 representatives to be won by their side, right? So they should have expected 0.45 times 13, which comes out to 5.85. And then I sort of generously rounded that up to 6 because it's fairly close. Or we could say 5 to 6, possibly. So they should have expected to win 5 to 6 seats, or we should have all expected them to win 5 or 6 seats. And the Republicans should have expected to win 54% of 13, or 0.54 times 13. And that was about 7.02, or approximately 7 seats, right? However, it was the opposite way around, right? Again, the Democrats should have expected to win 6 by winning 45% of the vote, and the Republicans should have expected to win 7, and it was actually flipped. So I would definitely say there's probably some suspicion, some foul play here, or at least some partisan effects on the maps that were drawn in the year 2002 that affected this 2010 election. So it's not, I won't call it exactly cheating, but I would say it's certainly not in the spirit of a fair and just democracy for that to be the case. Now let's go on and see the way this might have swung in the other direction, because of course, as we read in 2010, the Republicans drew the maps beginning in 2012 and onward for elections, and then they had an election in 2012 on their Republican drawn maps. So what happened in 2012? Well, we see that Democrats won 51% of the vote statewide. So in other words, 51% of the people in the state voted for a Democratic candidate. Everybody voted for candidates in their own districts, but 51% of voters preferred their Democratic candidate in their district. Similarly, 49% preferred their Republican candidates in their district. Now, what happened? What was the outcome? This one looks pretty wildly out of balance, right? It should have been about half and half, 6.5 and 6.5 each. So something like this kind of split, probably given that election. However, Democrats only won 4 of the seats, and Republicans won 9 of the seats. So that's sort of outrageously tilted in favor of the Republicans. So let's look a little closely. Do the calculation, 0.51 times 13. Democrats should have expected 6.6 seats, or maybe 5 to 6 seats is what they would have expected to get. And then Republicans should have expected 0.49 times 13, or 49% of 13, 0.637 or 6.37. So again, sorry, maybe I should have said Democrats should have expected 6 to 7 seats, and Republicans should have expected 6 to 7 seats as well. So it should have been a 6-7 split, most likely. However, it was a 4-9 split, which is pretty wildly out of balance with what we see here. It's a pretty even split in the popular vote throughout the state. However, the maps were rigged against Democrats in this situation, and the Republicans won pretty largely in this situation thanks to that. So this is a way to measure or to detect whether or not districting has been fair in a state or any other body of voters where districts are involved. So how might such a thing come about? Well, that's because the maps can be drawn in all kinds of different crazy ways. So courts in the U.S. will generally allow district boundaries, sometimes even convoluted boundaries, as long as they don't violate any specific laws and they meet the following 2 criteria. Right, so all districts within a particular state must have very nearly equal populations. So we need to divide up all the regions, all the districts with relatively equal populations. So that way no district has stronger voting power than another, right? We just saw voting power as a measurement between Wyoming and California. So within a state, you want to make sure your districts are all relatively equal in size. So that's one rule. And then the other one is each district must be contiguous. In other words, it has to be fully in touch with itself, right? So each adjacent member or household has to be, a neighbor. Basically, we can't jump over one district and be in the same district. In other words, we can't have a blob that looks like this and then over here, and then that's our district, right? Because that's not contiguous. This would make it contiguous if we included all the houses along this street or something like that to put them together. So all kinds of crazy stuff happens in these maps. I'm sure you might have seen things like this in the news or otherwise. So let's try to do an example here. We've got a fictitious state. There are 64 households in this state, or 64 voters in this state, we might say. It's 8 by 8. And half of the voters are Democrats. Half of the voters are Republicans. So 32 and 32. And the state has 8 total U.S. House of Representative seats. This is all made up. These are smaller, simpler numbers. They ask us to draw a map, which would first, with districts that should result in fair, proportionately representative congressional elections, right? This is all based on expectation and not necessarily fact, right? Again, what we said over here is not what should have been the case based on statewide percentages, but what we should have expected. And if we're close to what we expect, maybe off by a seat or two, then that seems okay. If we're not close to what we expect, well, then something's probably gone afoul in a pretty bad way. And I think both of these cases really were potentially, situations where the representation went awry, where what was expected wasn't met, and we could question the legitimacy of the districts in that situation. So anyway, let's try to draw a fair map first, okay? So if we zoom in and look at this, we realize we've got blue. It's hard to see because it's been highlighted already. We have blue and red households. Those are these little V's, or we'll just call them voters. They're not V's, but they're gammas actually, but they're like little houses maybe. So red is Republican and blue is Democrat. And what I've done is gone through and I've already pre-made these districts because it's kind of hard to do it in a fair way. So we should just count up to make sure that what I've chosen here is actually we're going to expect a pretty fair result. So let's look at all these different districts. Some districts should be pretty easy to sort of recognize as a Democrat stronghold or a Republican stronghold. So we have Republican seats, Democratic seats, and we're going to tally up what is most likely going to be a democratically won seat, and then we're going to have toss-up seats. In other words, tight races, places where there's a pretty competitive race that happens. Okay, so in the effort to make this contiguous, I had to accept that there were going to be some toss-up seats, and I had to accept that some areas were just going to be fully Republican and some were going to be Democratic. So I'll go from top to bottom, and I'll move left to right as I go from top to bottom. So I'll start with this district right here in the top left. When I look at this district, it includes all of these voters of these households right here. All of those are blue except for one Republican voter. So even if not all the Democratic voters showed up, most likely this is going to be a win for a Democratic seat. Okay, so we'd expect that to go to the Democrats. Let's move to the right by one. Now this is this region, right? This sort of funny snake-looking region right here. Again, it's contiguous, right? They're all adjacent to each other. That's one rule. And each one of these blobs, if you look, or these highlighted strips and sections or districts, they all contain 8 voters total too. So they're all equally represented, so that we're meeting both criteria with contiguousness and equal numbers of voters in it. So this one looks like it's a toss-up, right? We have 1, 2, 3, 4 Democrats and 4 Republican voters in this district. So this is going to be a tight race for whoever is running in here, right? So there's one to the toss-up category, and we'll call that the tie, right? The sort of, this one's going to be settled by the voters, and but it is fair. It's 4 versus 4 in terms of the number of voters in the district. Now we move to the right. This is a Republican district, obviously. There are no Democratic voters there. So we can give a sure seat to the Republicans, or a very likely expected seat to the Republicans. Now the next region on my way down is this one. Next district. This looks like a very strong Republican district, right? This tan highlight right here, orange highlight, whatever it is. So there's only one Democrat in it. I think that's probably expected to go to Republicans. So when I drew this map, I had to keep picking certain regions so that I could, give Republicans the same share of guaranteed seats as I did to Democrats. And then whatever was left, I had to leave as a fair toss-up. And I wanted to make sure I left it very fairly as a toss-up. And I think we'll see that that's the case. So now my next region down is this one. It's these voters. And when I look at this region, I realize that I have 1, 2, 3, 4 Republicans in it, and 1, 2, 3, 4 Democrats in it. So that's a fair toss-up, 4 versus 4, Republicans to Democrats. So we put another one in the toss-up category. And then I look at this district. This again looks like 4 Democratic voters and 4 Republican voters. So that's another toss-up, another tight race. Okay. Now I move across, I've got this region. And this looks like another 1, 2, 3, 4 versus 4 toss-up region. And then my very last region is this one, the only one I haven't counted up yet. And this is all Democrats in this region, actually. So this looks like a sheer Democrat seat. And I would say that this, if we districted this very square state with very square districts, or not square districts, but with a very regular layout, and then a bunch of these funny squirrely little districts, I would say that for as wacky as these things look, this is a pretty fair scenario, right? We've got 2 guaranteed seats for each party based on these districts, a strong Republican district, a strong Democrat district, and then we've got 4 toss-up seats. In each one of those toss-up districts, and where we're competing for a seat, we have 4 of each type of voter, Republican or Democrat. So it's going to be a pretty good head-to-head election. It's going to kind of result in which party turns out stronger. So this would be an example of due diligence in trying to draw a fair map for equal representation for each party. Now that's part A. Part B says, let's draw a map that unfairly favors Republican representatives in congressional elections. So we need to do this all over again, right? So I'm going to start with a fresh map. This is my cheater map. I'm going to do this in favor of Republicans. And it turns out the way that this map is laid out, that if we just choose districts for each row, so I'm going to use highlighter to do that. If we just choose districts by row all the way down this state, these horizontal strips in the state, what we're going to see is there's going to be a pretty slight imbalance. It's not the most cheatery map as we could come up with, but it's pretty close, right? But it's going to be slightly in favor of Republicans, and they just say make one that favors Republicans. So let's look at the number of Republican voters in each map and the number of Democratic voters in each one of these districts, and we'll say who's the expected winner, Republican or Democrat, when we see that. So in this case, we've got 1, 2, 3 Democrats versus 5 Republicans in this district. So it's 5-3 Republicans to Democrats. So we're probably going to win. That's probably going to be won by Republicans, right? As we expect that Republicans are kind of favored in that district based on the layout of the voters. So that's one win for Republicans for a district. Now let's keep going down the list here. Again, 3 Democrats in this row with 5 Republicans. So 5-3. So that's another likely win for Republicans. We look across this one, and again, it's 5 Republicans, 3 Democrats. So we start to think to ourselves, this can't hold out much longer, right? Because the Democrats, they've got to be somewhere, right? There's an equal number of Democrats and an equal number of Republicans. But what happens is this idea of packing and cracking, right? So we're going to pack all of the Democrats into a single district, right? And then we'll give them that district, right? It looks like we have one Republican here with 7 Democrats. So of course the Democrats win this one. However, it's not really to their advantage because they could have used some more of their Democrat voters elsewhere in other districts so that they won more seats, right? I'm looking down at the very bottom. So what we do is we, if you want to pack the map or rig the map to favor your party, in this case, Republicans, or that's what the question's called for, then this is the way to do it. Again, we have another row, 5 Republicans, 3 Democrats. And though this might be tight, it could turn out, it could come down to voter turnout. The Republicans now have 4 seats that are leaning in their favor, with 5-3 voter scenarios. And again, we get to a 5th row, again, another 5-3 scenario for Republicans. And it looks like, where this map is now no longer fair. There are 5 districts that favor Republicans, and there are 3 districts that favor Democrats. So here's a 3-5 for the Democrats, and here's another 3-5 for the Democrats. So at the cost to the Republicans or to the map maker of giving one strong district to the Democrats, you can otherwise split them up. You pack them all into one district, and then you crack the rest of them and you split the rest of them up so that you can accomplish, districts that are more in favor of your party. So that's the idea with gerrymandering, right? So in this situation, the expectation is that Republicans win 5 seats and Democrats win 4. And when the voters are half and half, win 3 seats actually. When the number of voters in the state are half and half, it just doesn't seem fair that one party is going to get more than half the seats than the other one. That's this isn't a big cheat of a map. What we could really do if we wanted to make this even more in favor is make another district that's 1 Republican, 7 Democrats, and then we've really packed in the Democrats, and we'll probably take another seat away from them and give that to Republicans. And that's gerrymandering in a very simple form using these square fictitious states. It's an interesting exercise to do. And what you'll do in the problems is you'll just pick the ones that, they'll say pick a map that favors Democrats or Republicans or one party over the other, and you'll sort of spot which one based on its districts does that. So that's it. That's fairness of voting, election power or voting power, and then districting all in a nutshell. And that completes chapter 12.